Hello everyone, my name is Souvik Das and I'm here to present our paper on practical labs for teaching SDN security. I'll first briefly describe the concept of software-defined networking and some of the security issues associated with it in alignment with its practical industrial use cases and how they may be better addressed through a set of practical lab exercises that we have proposed for students at the graduate level in academia. Traditionally, computer networks had both the control and the data plane programmed right into the same networking device, such as a router, switch, firewall, and network load balancer. The motivation behind such a design was to build a survivable network where each node functioned autonomously, such that they established the consensus for network control and communication through frequent negotiations with the neighboring nodes. However, over the time, the design proved to be both computationally and financially expensive, with very little flexibility in introducing new services into the network. To that end, the emergence of software defined networking, or SDN, was a paradigm shift, since it enabled the control plane to be separated from the data plane in the networking devices. It not only proved to be a means for overcoming the limitations of the traditional networks, but also at the same time gave network operators better control of their network and enabled them to introduce new and customized network services in a timely manner. As with most new technologies, new challenges arise. In case of SDN, security stands at the forefront of these challenges. The market forces today put tremendous pressure on vendors to introduce SDN solutions into their products, as well as on network carriers to deploy SDN based network services so as to differentiate themselves from their competitors. However, this happens often without necessarily paying due attention to security implications of this new technology. As a result, it exposes a range of network and application security issues today. The concern for some of these issues is novel to SDN's paradigm and often requires adopting advanced strategies such as moving target defense, closed loop automation, and machine learning in practice. While the domain of solutions to these issues keeps expanding with the increase in the variety of SDN applications, the concern, however, remains fundamentally aligned with the networking and cybersecurity concepts that are taught at the graduate level in academia. This motivates us to introduce the concept of SDN security to the students as a sequence of 8 hands-on lab activities that address one or more of the cybersecurity issues, including but not limited to denial of service, unauthorized access, configuration issues, man in the middle, network sniffing, and side channel vulnerabilities. I would now like to briefly describe the framework that we have used to design the activities in our lab manual and the methodology used to deliver them to the students. As with most labs, each activity in our manual comes with a set of guidelines to help students perform various tasks to complete the activity. Along with these guidelines, each activity is provided with various technical hints and reference materials included in the manual to help students easily explore the concepts required to perform these tasks. These include comprehensive tutorials to help students explore the features and capabilities of the SDN controller that are relevant to these activities, alongside other software toolkits required to perform them in an end-to-end manner. The manuals also include guidelines for students to debug and test their approach as they make progress towards perfecting their solutions. Furthermore, instructors are separately provided with a reference manual that contains a demonstration of an approach to implement the solutions in each activity. Each activity also includes a hackathon section in which students are asked to draw suitable inferences from a given variation to the problem scenario and potentially design a solution of their own using suitable heuristics or in consultation with the published solutions suggested in relevant academic papers. The goal of this section is to help build the level of competence in graduate students that is required to practically address the many variations to these problems which they would inevitably face as future industry professionals. We intend to introduce this section in the curriculum by initially motivating students to attempt it for bonus points. As a precursor to the proposed lab activities, the manual also includes a couple of warm-up activities that illustrate how concepts of SDN could be applied in the practical sense before moving forward to address its complex security issues. Lastly, to ensure that the students have the appropriate software resources to perform these activities, we have bundled a set of software toolkits that are relevant to these activities in a virtual machine or VM configured to run on VirtualBox. The composition of this VM is shown in the top figure. We recommend students to use this VM as their workspace for end-to-end execution of the lab activities. We believe that this will be especially useful to the students who do not have the knowledge of the content or the required resources to set up a workspace themselves. The figure at the bottom shows a view of an SDN deployment that can be simulated in our VM workspace. In this, there is an SDN controller that controls 3 switches in the data plane. Now, coming to the first lab, unauthorized access by compromised controllers. In practice, network control is often distributed across multiple SDN controllers for scalability and resiliency purposes. Inspired by that, we present a scenario in this lab where such controllers are deployed, each with the task of controlling a specific section of a network of underlying SDN operated switches. The students are given a set of flows for paths between network hosts located across these switches and are instructed to deploy and configure the setup in their workspace. We then present a scenario where an adversary hijacks one of the controller's configuration and successfully injects a malicious flow into the network. This new flow essentially reroutes the traffic for one of the network paths through a network host that colludes with the adversary to hijack communication along that path as shown in the figure. As part of the hackathon, the students are first given certain hints to produce this man-in-the-middle attack scenario in their workspace, and then they are asked to refer to the Byzantine general's problem to try and come up with a possible solution to detect the compromised controller and make the necessary changes in their original solution to implement it. The assumption here is that configuration of at most one of the controllers will be different from the others with regards to the flows that are installed in the underlying topology at any given time. Now, coming to the second lab, unauthorized access by unauthorized applications. The paradigm of SDN enables multiple tenants to operate on the same network. A tenant here could be an organization that shares the same underlying network in practice. In this lab, we present a scenario where a tenant exists as an application module inside an SDN controller and uses its resources to install network flows. It is assumed to be trusted because of its locality in the network, which, however, gives it the potential to cause unauthorized operations in the network. Given two tenant applications foo and bar, the students are instructed to develop a controller module to broker the task of installing flows for them. Given the conflicting nature of their workflows as shown, the students are required to adopt a priority or integrity heuristic across them in order to break ties between their operations such as shown in the figure. For the hackathon, the students are required to implement an access control scheme in which the tenants are further required to obtain permission from the broker for performing different flow operations such as get, add, and remove based on a set of flags assigned to them. The premise of this lab is that given a proper guidance system, unauthorized operations from otherwise trusted tenant applications could be effectively avoided. Now, coming to the third lab, DOS attack detection and mitigation. The concept of denial of service, or DOS, is not new to the literature. It describes a scenario where the nature and volume of traffic overwhelms the network and its applications. The fact that networks in general are designed to be reachable is often exploited by adversary to launch these kind of attacks. In this lab, we present a similar scenario in a simulated manner, and the students are given 3 different methods as shown in the figure to detect the attack. Some of these methods are inspired by relevant academic papers which they can refer to for their better understanding. Otherwise, they may just follow the guidelines given in the manual to implement them. The latter of the methods, which is resource-based, is included as part of the hackathon. In this part, the students are first required to choose a simple file storage application of their choice and deploy replicas of it with identical content in an SDN operated network. Inspired by a technique called adaptive bubble burst, they are required to effectively spread the traffic across those replicas in an adaptive manner based on a heuristic over the load incurred by the individual replicas at any given time. The premise here is that adaptively scaling the traffic across the replicas would reduce the impact of a DOS attack. Now, coming to the fourth lab, network configuration issues. In most SDN settings, the northbound interfaces, such as REST interface, is often designed to be open-ended so as to welcome a large variety of applications. Unlike tenants living inside the controller, these applications can control parts of a network from outside the controller. Given the nature of the interface, a simple access control scheme may not be sufficient to cover the wide range of objectives that these applications may have. To that end, we present a scenario where such applications fulfill their objectives through a set of well-defined network policies, such as shown in the bottom figure. However, that alone does not prevent conflicts from arising as a result of these policies. To alleviate this problem, students are instructed to implement a northbound manager application to manage and mediate the installation of policies in the network. Students are given the option to use an interface of their choice to enable other applications referred to as clients to communicate network policies with the manager. They are required to address this problem using two different approaches: a proactive approach, where they resolve conflicts between incoming and existing client policies, and a reactive approach, where they do the same between managed policies, such as those of clients, and unmanaged policies or flows that are already deployed in the network. As part of the hackathon, we present a scenario where a set of network policies, which even though may not formally conflict, but potentially result in a network cycle. Given a dense and wide SDN operated network, such as shown in the figure, students are required to come up with an efficient way to detect such a cycle. Now, coming to Lab 5, ARP Spoofing Attack Mitigation. Address Resolution Protocol, or ARP, is widely used for producing a mapping between IP and MAC addresses in network switching domain. However, it is known to be vulnerable to a range of spoofing attacks such as cache poisoning attacks, leading to man-in-the-middle or simply impersonation, or even a form of denial of service attack. Inspired by a survey on such attacks on ARP and their possible solutions, we have tried to narrow the range of such solutions down to three stages that we believe could help better capture the related strategies as a lab exercise. In the first stage, students are instructed to develop a controller module to detect a mismatch between Ethernet and ARP headers in network packets to prevent possible man-in-the-middle attacks. Next, they track host identities as learned through prior communication to prevent possible impersonation attacks. Lastly, they track ARP requests and response messages to detect unsolicited ARP messages to further harden their solution. As part of the hackathon, we present a scenario where we allow host location to change under certain restrictions. Students are hinted to design suitable heuristics, such as based on entropy of change in location, required to effectively address the scenario. The manual includes comprehensive workflows to test their solutions at each stage and scenario. Now, coming to Lab 6, Moving Target Defense. In practice, communication between network hosts depends on two things. First, the ability of the hosts to identify each other, and second, the ability of the network to identify the paths between them. Typically, services such as DNS are deployed and a routing process such as Dijkstra's shortest path algorithm is employed to help achieve that. However, the knowledge of the presence of these services and the processes in the network gives an adversary the ability to track the identity of the network hosts and predict the paths between them. This information could be exploited by them in the long run to stage a well-planned attack on the network. Moving target defense describes a range of mechanisms to introduce unpredictability in the network to address this problem. In this lab, we present two different scenarios. First, where an adversary tries to learn host identities, and second, where it tries to learn the path between them. Students are presented with two different approaches based on solutions from relevant academic papers to address these scenarios. These are namely random host mutation and random route mutation. In the former, they develop a controller module to randomly and frequently change the identity of hosts in the network, and in the latter, they switch between the paths between hosts in a similar manner to give an adversary very little scope to stage an attack. The latter is included as part of the hackathon. The figure on the right shows the scenario in the presence of an adversary. Part of the lab is for students to ensure that their solutions achieve the required unpredictability without affecting ongoing communication in an SDN operated network. The test workflows given in the manual are aligned with this requirement. Now, coming to the seventh lab, ML-based Network Intrusion Detection System. Networks are constantly under the threat of malicious attacks. However, the heuristics used to address them today are not suitable for all network scenarios. They only help cover a limited range of variations to these attacks. To that end, network designers employ learnability in the design of their network intrusion detection system or NIDS solutions to predict malicious behavior. The premise here is that the use of machine learning or ML helps capture the features of a malicious traffic that most heuristics often cannot. In this lab, we present a scenario where an SDN operated network is faced by a TCP SYN flooding attack, and we instruct students to implement an ML-based NIDS solution to address this problem. We have identified certain steps for students to follow that at a high level includes: first, a way to effectively capture network flows from ongoing traffic, for which we use Argus by Quotient. Second, a way to effectively collect and store the flows using Elasticsearch, a big data toolset. Third, a way to retrieve, learn, and classify them, for which we recommend using Elasticsearch API and scikit-learn package on Python, along with a suitable training dataset. And lastly, a way to take action on the detected malicious traffic, for which we recommend using controllers REST API, with all these steps configured to work in a pipeline manner as shown in the figure. As part of the hackathon, the students are required to try different classifiers and report their performance on the test workflows given in the manual. Now, coming to the eighth and the last lab, closed loop automation. Closed loop automation is a high level term used for introducing a range of feedback mechanisms to seamlessly automate control across parts of a system and its resources. In an SDN operated network, a controller could receive feedback for its various operations from mainly two different sources: the applications that are running over it and the devices in the underlying network. In this lab, we present two different scenarios that try to address certain bottlenecks, such as in the functioning of an application in relation to the underlying network that helps run it. To paint a better picture of a scenario that might benefit from such an automation in that regard, we have chosen Apache Flink, a distributed stream processing application, for the activities in this lab. In the first scenario, the students are given a streaming workflow on Apache Flink that listens to streaming data from a given source application, transforms it into application level records, and sends it across to a given sync application hosted on the same network. By varying the parameters of the source application, we are able to generate traffic that may either vary in volume or in the quantity of records produced, or both. Students are instructed to configure a quality of service mechanism using SDN to aid such streaming endpoints in processing occasional large bursts of such application layer traffic. The second scenario is given as part of the hackathon that requires them to deploy an SDN overlay network, such as shown in the figure, and use its underlying resources to support the same streaming workflow. Part of this activity is to figure out a way to adaptively migrate streaming traffic across nodes in the overlay and ensure that all the unused links in that network are scraped afterwards as a measure to avoid potential side channel vulnerabilities without disrupting any ongoing network communication. In conclusion, different deployment scenarios require different solutions to address the network and application security issues related to SDN in practice. We have developed a number of security lab activities inspired from realistic and practical SDN network deployment scenarios. Our lab provides students with a structured framework to try out new solutions that they may come up with either by themselves or in consultation with relevant academic papers. Lastly, we plan to include these lab activities in our graduate level network security class to get feedback and improve on them. I hope you enjoyed this presentation, and now I would like to hear your thoughts and opinions about it. Thank you.